All right, a couple little things. One loose end, I want to tie up two little loose ends from last time. One is, after I introduce Kirchhoff's rules and matrices, you guys suddenly get overzealous with Kirchhoff's rules, and you want to use them whenever you can, and you want to make a matrice whenever you can. And you forget that it's actually easier not to when you have a circuit when you don't have to use Kirchhoff's rules, so it's not overly complicated. So please remember that you don't have to use Kirchhoff's rules. Do not get overzealous. Second, I want to walk through a graph, which I thought we actually put on the board last time. We, of course, start with today's desktop picture. Today's desktop picture is a picture of Ryan. I just thought it was a great picture of Ryan. She was playing hide and go seek, and I caught her opening her eyes and looking around while she was counting to 20, which is cheating, hence the expression on her face. All right, so we have this picture, which is a picture of a simple circuit. We have the EMF of the battery, the internal resistance of the battery, and the terminal voltage across from A to B, and we have a resistor from C to D. We've already looked at this. We already looked at this graph as well, showing the electric potential difference as a function of where we are in this circuit. Now, everybody looked at this. You said, oh yeah, look, the electric potential difference goes up as we go across the battery. Look, it goes down as we go across the resistors, if we're going in the direction of the current, right? In other words, if we were to draw the loop in this direction, this circuit would follow, and we would have a positive electric potential difference across the battery, we would have a negative potential difference across the two resistors. However, if we were to draw this, if we were to go through the loop and do the loop this direction, opposite the direction of the current, it would be like going the opposite direction across this graph. We would be going this way across the graph, which is why when the loop direction and the current direction are in opposite directions, you have the potential difference goes up across the resistor. And if you're going from the positive to the negative across the battery, then the electric potential difference goes down. There seemed to be some confusion as to why the electric potential difference would go down when we're going opposite, or I'm sorry, the electric potential difference would go up when we're going opposite the direction of the current. Does that help? Okay, good. It just seemed like something we should take a few moments and go through. Now, we did not get to discharging a capacitor last time because your brains became full. So let us now fill your brains again because they leaked a little. Here we go. We had a capacitor. Last time we were charging the capacitor through a resistor. So we had a capacitor, we had a battery, we had a switch, and we had a resistor. We flipped the switch and we charged the capacitor. So now what we're going to do is we're going to say we've already flipped the switch. We now have positives across on one plate of the capacitor and negatives on another plate of the capacitor. And we are going to, this time, we're going to remove the battery and then close the switch again. So what we're going to do is we're going to take out the battery. Well, actually, let's do this first. So we already know, the electric potential difference around the loop is equal to 0. If we go this way around the loop, we get, walk me through it, please, Yucha. Yeah, we're going this way around the loop. The electric potential difference around the loop, we're just going piece by piece.
Which way is the current?
Okay, which way is the current? Fair question. Through the resistor on the top, which direction is the current? Let me close the switch because otherwise you would say the current is nowhere. So let's just do this. The current, we've closed the switch. Through the top resistor is what direction, Millie?
The right.
To the right. Through the top resistor, the current is going to be going this direction.
So R will be negative.
Okay, so I'll put that one last. Here we have the electric potential difference across the resistor.
Battery would be positive.
The EMF of the battery, again, positive.
And then the capacitor would be negative.
negative because we're going from the positive to the negative, which is that the electric potential difference is going, the electric potential is going to go down. All right, so we have 0 equals the EMF minus, what is the equation we're going to use for the electric potential difference across the capacitor? Where does it come from? Match.
Current resistor or whatever.
Sure, we can do the resistor first. Capacitor or resistor, I don't care.
Was it just IR?
This one's just IR. Good. Match. The other one? Start with the equation for capacitance. It's the easiest way to do it.
Is it Q over something?
Q over something. What is the something? Hillary?
B.
The electric potential difference. Therefore, the electric potential difference equals the charge over the capacitance. Therefore, we have Q over C. This is what it looks like when it is charging. Now, we are going to remove the battery. So we're going to remove the battery. And we now have the resistor. We have our switch. And we have a charge on the capacitor and our resistor. Now, when we flip the switch, basically what we have now is current flowing. And we're going to have the exact same situation, but we've removed the battery. So now we have 0 equals negative Q over C minus I times R. Okay, we'll work with that equation in just a little bit here. I want to actually start out here now with the limits. So what do we know at t equals 0, which is when we close the switch? So at t equals 0, we close the switch. What do we know, for example, about charge? Charge initial. What do we know about that? Mr. P?
Is that 0?
The charge initial is not going to be at 0. Otherwise, this would not be discharging a capacitor through a resistor. If the initial charge on the capacitor were 0, nothing would happen when you close the switch, right? 0.
Would it be like just big Q?
Big Q. And what do we know about that?
It's like the max.
It's going to be the maximum because as soon as we close the switch, little charges from our capacitor are going to start moving around the circuit in the form of current. Okay. So Q initial is Q, it's just going to be big Q, which is our maximum charge. What about current initial? What is the current initial? What do we know about that? Zach?
0.
It's actually not going to be 0. Because as soon as we flip that switch, current is going to start to flow. What's going to happen to the electric potential difference? Actually, we'll start with this. What's going to happen to the charge across the capacitor as a function of time, class? It's going to decrease. What then is going to happen to the electric potential difference across the capacitor as a function of time? It's going to decrease. So what do we know then about the current through the resistor? It's going to decrease as well. Notice the electric potential difference across the capacitor and the resistor in this situation are actually going to end up being just equal to, well, they're going to have the magnitudes, but they're going to have equal magnitudes but opposite directions. Therefore, the current is going to start at its maximum value, just like the charge, and decrease. So the current is going to also start at its maximum value. Okay, what about at time t is approximately equal to infinity? What do we know about the charge final? Tim, charge on the capacitor final.
Would just be little q?
It's actually not going to be little q. That's what it's going to be at some time in between 0 and infinity. What's it going to be at infinity?
0.
0. After a long time, there's going to be 0 charge left on the capacitor. What about current final? What do we know about current final? Gary?
Would that also be 0?
It's also going to go eventually to 0. So those are the limits. We start out at the maximum charge, we start out at the maximum current, and slowly, over time, depending on the time constant, how long it takes, both will decrease to 0. So now, our goal is to solve for charge as a function of time and current as a function of time. Again, these are things that you are responsible for being able to derive. Let us rearrange this equation. We get current times resistance equals negative Q over C. Let's get RC over to the other side. Current is equal to negative Q over RC. The definition of current, Emily, what is the equation for current? There are several options. Just give me one. Give me any equation for current. Delta V over R, right? That would be in terms of voltage and resistance. I'm looking for more the definition of current. Look.
dq over dt.
dq over dt, by definition, is the derivative of the charge as a function of time. So dq over dt is equal to negative q over rc. Let's bring charge over to the other side and bring dt over to the other side. So we get dq over q is equal to negative 1 over rc times dt. We take the integral now of both sides. We have the integral of 1 over q with respect to charge is equal to the negative of the integral 1 over rc dt. Limits. What are the limits on, for example, q? Where does it start and where does it end? Charge. Tyler.
Big Q starts with big Q, and is 0.
Right, but remember, we're ending at some time t that is in between 0 and infinity. So what's
So it starts at little q, or ends at little q?
ends at little q, and little q is what we're trying to find, right? That's going to be the charge as a function of time. What about time? What is time initial? Mohit.
0.
0 and the time final?
Just t.
Just t. Again, this is the time at which we have some certain charge, which we are solving for little q. Okay, so now, let's see. Left-hand side, integral of the 1 over q with respect to charge, Stacey? The natural log of q, and that again is going from big Q to little q. So we have natural log of little q minus natural log of big Q. So we have the natural log of q over big Q. Right-hand side of the equation, what can we do with that? Sarah Jane Jones.
You can take out R and C.
Negative 1 over RC times the integral of dt from 0 to t. Let's keep going, Sarah Jane.
So the integral is just t.
So we have negative t over rc. Negative t over rc. At this step, Dorfstetter, what do we need to do? Raise everything to the e. So we have e to the natural log of q over big Q is equal to e to the negative t over rc. So on the left-hand side, we have little q over big Q, which is equal to e to the negative t over rc. In other words, the charge as a function of time is equal to q, which was the initial main charge, times e to the negative t over rc. Let's check the limits. The initial charge, Michael, was what?
Q, big Q.
Big Q. So at time t equals 0, Michael, e to the negative 0 is equal to 1. So we just have the Q initial is going to be equal to big Q. Q final is equal to what, John?
0.
0. Negative e, or e to the negative infinity, John?
0.
0. So we have just 0. Great. Works out. We also need to figure out the current. How are we going to figure out the current? Hamza.
We start with dq over dt again.
So we have current is equal to the derivative of charge as a function of time. True. And we have the equation for charge. It's equal to big Q e to the negative t over rc. Current as a function of time then is going to be equal to, please take the derivative, Nick.
Is it e to the negative t?
Negative t over rc.
Okay, so it would be negative big Q over RC e to the negative t over RC.
Okay. Negative big Q over rc. Okay, so let's come back over here. If you look, we know that the charge initial in terms of the battery. Okay? What is the charge initial equal to? Coming all the way back here. Okay, so let's come back to, we need to get to the capacitance, right? So the charge initial is going to be at time t equals infinity before this is after charging the capacitor. So what is the current after we've charged the capacitor, class? 0. If the current is 0, what's the charge equal to? E times C. So Q, the charge initial, is going to be equal to E times C. So we get the current as a function of time is going to be equal to E times C over RC, a negative E to the negative T over RC. Capacitance cancels out. Current as a function of time equals negative E over R times negative T over RC. What's E over R? Yes?
Did we lose a negative when we solved for Q?
When we solve for Q.
Oh, never mind.
Okay. Okay. E over R. Okay.
What's the maximum current?
That is the maximum current, which is the current initial. So the current as a function of time equals negative current initial times e to the negative t over RC. I'll just note this negative simply means that it is now discharging. The reason that is negative is because the direction of the current flow now is opposite the direction of what it was before. Because we now have positive charges here and negative charges here, which are causing the current to flow opposite the direction the current was flowing when we were charging the capacitor. That's what that negative means. Charge in coulombs as a function of time in seconds. What does the graph look like? Flat. Start with the limits. Where does it start?
It starts at zero.
Somewhere in between. Help them out. Where does the charge start? We're trying to create the graph here. Motive.
Big Q.
Big Q. It starts at big Q. That's our initial. And where does it end? Bill. The charge final. Discharging the capacitor through the resistor. Zero. So it ends at 0. What does it do in between? What does Q times e to the negative t over RC look like? Show me with your hand. Right. You all know, you've done this many times, it's going to look something like this. Okay. Now we have the current in amps as a function of time in seconds. The initial current is actually negative, so I'm going to have it down here. This is the current initial, which we know is E over R. It ends with a current of 0. Show me with your hand what it looks like. It's just, it'll look very similar, only reflected over the t axis. So,
Why is E over R the initial?
why is E over R the initial current? Fair question.
Wait, no, that's not my question. My question is why is Q initial E times C?
We'll start with that question. We come back to, we need to know the charge on this capacitor. The charge on this capacitor was determined by the battery the battery, essentially, right? So we have the battery in this circuit. After a long time, the current goes to 0, agreed? As we're charging the capacitor. So then we remove, so then current times resistance is 0. So you add Q times C to the other side, and the charge initial is just going to be E times C. So that is the charge initial.